I'm assuming if you've clicked on this video, you've watched my main channel video of the air-powered plane. And what I thought I'd do is go through the video and do sort of a deep dive into a lot of things that I had to edit out. A bit more information on some of the points. So let's get started. When I was a kid, I had one of these Air Hogs planes that was powered by a small plastic engine. This engine used compressed air as its fuel. Stopping already. This plane I found on eBay. It was listed for £20. What's that, about $30? And it was had 5 days left on the bid. And I messaged a guy saying, I'll come and collect it. He lived 5 miles from my house. I'll come and collect it and give you £30 cash today. And when I turned up, he was like, are you sure you want to pay this much for an old toy? And this thing was in brand new condition. It still had like the little wire tags attached to it. And I was like, mate, take the 30 quid. This thing is amazing for me. I didn't quite make it sound that good. I was just like, oh yeah, I'm just collecting toys. But yeah, I managed to get a really good deal, and it's perfect for this video. And I remember pumping it up to high pressure with the small included pump before throwing it into the sky and never seeing it again. And I actually lost my original one on the roof of a school. I was flying in a field and it disappeared and landed on the roof. Stayed up there for a couple of days and then probably someone else got it back. But the same as losing it. Yeah, same as it flying off into the distance. Ever since then, I've wanted to build my own version, but a little larger. So I started 3D printing some lightweight aerofoil ribs in. So this is the first time I've printed with ABS in probably 5 or 6 years. And I was very surprised how well it printed on the Prusa Mark III in the enclosure. I didn't need to put any acetone or ABS like sludge on the plate, which is what I had to do back in the day. A lot of people were asking in the comments, why didn't I use lightweight PLA? And the reason, the main reason was the temperature resistance for when I iron on the covering film. But also, lightweight PLA is a lot more bendy and a lot weaker than ABS. So I think it depends on the structure. If I was printing like a more solid part, like a more 3D solid part rather than a plate, then maybe lightweight PLA would be better. But for this, to reach the same amount of strength, I'd have to make the little structural bits a lot thicker. So I think in the end it would probably weigh the same as the ABS. Because if I printed this rib out of lightweight PLA, it would just be way too bendy. I mean, I have one of the test ribs here, and see how bendy that is in ABS. So if that was out of PLA, or lightweight PLA, sorry, there's no way that would be strong enough. Good thing is with ABS as well, it flexes quite a bit before it breaks, which I think probably helped it during the crash at the end of the video. Spoiler alert. ABS plastic that will make up the internal structure of a... Oh, the other thing with this carbon fibre spar, so when you buy carbon tubes, or at least when I seem to buy them, they always come with a 1mm wall thickness. So this is 10mm outside diameter, 8mm inside diameter, and for 1 metre piece it weighs about 50 grams. It's quite strong, but it's quite heavy at 50 grams. But I managed to find somewhere that sells these spars, which are 0.5mm wall thickness. So it's 10mm outside, 9mm inside. So it's half the weight, 25 grams. It's a bit bendy, but for radio controlled plane, it's plenty strong. So I managed to shave 25 grams off finding this spar. And also these 3mm rods, which I use on the leading edge of the wing. 2 of these, there we go, 2 of these are the same weight as one of these spars. And check out how bendy these are. Look, these bend like pieces of spaghetti. Now, sure, if you space them apart so they're in tension and compression, you get a bit more strength. But like in a wing, there's not much vertical height to play with. So yeah, using this spar was just far more easier and about the same weight. Wing. I could have used other materials like balsa wood or carbon fibre, but those are more difficult to manufacture and wouldn't save a significant amount of weight, as these ribs are very thin. Once glued to the carbon fibre spar, I glued a carbon rod to the leading edge and a carbon strip to the trailing edge, as the wing will be covered in a lightweight film, so these will help hold the aerofoil shape. Now, I've never covered a wing like this before, so I had a quick read of the instructions. This stuff is very thin and delicate, so it creases easily. Funny thing with this covering film, so I have some white film as well, and basically it has a backing to it, which is what I'm peeling off there, and it has the actual covering film. And I think the white stuff that I have, it's like a clear backing, and then the white, the white covering film. So when you peel them apart, you can see, oh, this is the bit that just protects it, and this is the actual film. Whereas with the clear stuff, they kept the backing part clear as well. So you roll it out, peel them apart, and it's like, which is the covering film? So I had to cut a little square off each time, and then iron it to a piece of balsa wood, and one of them would like shrink and melt and shrivel up, and then one of them would stick properly. And it was a nightmare trying to figure out which one was the backing and which one was the actual film. But on the underside, it has a heat set adhesive, which can be ironed onto the wing structure, which is why they're printed from ABS due to its high melting point. Once ironed onto the ribs, a quick blast with a heat gun will shrink the film down to create a smooth wing surface. But there are some issues. The first being the ribs at the wing tip bend inwards due to the tension in the covering film. And this tension also causes the airfoil to shrink between the wing ribs, making an inconsistent profile along the wing span. Plus, I may have held the heat gun in one position for a little too long, causing the covering film to melt. I just want to talk about wing design quickly, as this is the fourth air-powered plane I've attempted to build and fly. The first plane I built was the heaviest, but it was the heaviest, but it isn't the heaviest now. This latest plane is actually heavier than this first version plane that I have, and that has a 2 meter wingspan as well. The reason for it is these wings are actually heavier than foam wings. I reckon, so one of these wings is, I think it's 99 grams. It's like just under 100 grams. So obviously, so nearly 200 grams for the whole 2 meter wing. But I reckon I can build a foam wing for lighter. I could probably shave, I reckon I could shave off 50 grams. I reckon you can make a 2 meter foam wing with it's a 20 centimeter cord. I reckon you could probably make that for 150 grams or less, maybe. But the foam wing is very difficult to get a really accurate airfoil profile. So the reason why I went with this one, first of all, because it looks cool, which for YouTube is important sometimes. But also the airfoil profile, I was hoping it was going to produce much better performance. It would be interesting to see if I made this wing as close as I could to the same profile, but with foam, to see if it would fly, or see if it would be much lighter and then potentially fly longer. The other thing that made this first plane a lot lighter was that the bottles are glued together, glued bottom to bottom. So there's no, if you've watched the full video of this, later on I joined two bottles with a nylon bolt, which maintains the bottom of the bottles, which is the 5-piece thing that it sits on, which is much thicker plastic than the rest of the bottle. So cutting the bottoms of the bottles off and gluing them together saves a lot of weight. However, when I did it on this one, I tried it multiple times, and it was very difficult to get a leak-free seal between the bottles. I tried many different glues, and I think, well, it is possible because lots of people do it when they build water rockets and things. For some reason, I couldn't get it to work, but maybe that's something I need to explore in the future to save a bit of weight. Used a very similar wing to what I'm building now, though it was constructed from foam board. And despite the plane using a very inefficient engine, it actually holds my personal best flight time record of 16.5 seconds. Whereas my last air-powered plane, which had a far more efficient engine and was much lighter, only flew for 8 seconds, which is partly due to it hitting a fence. But if the wing had a higher lift-to-drag ratio, it may have cleared the fence. I've been trying to make these planes lighter and lighter, whilst trying to make the engines more and more powerful. But what I haven't been looking at is the drag caused by the aircraft. The last wing I built was very light. This last plane I think was about 250 grams. The new plane is just over 500 grams. I think it's about 520 grams. So it's double the weight of the last plane, but has double the bottles. And has radio control on it. This one didn't have radio control on it. So what would be interesting is if I had the old engine on this plane, would it fly a lot better? Well, it should fly a lot better because the new engine produces so much more power. But how much longer would it fly compared to the new plane? Obviously, without radio control on this thing, maybe a bit risky because it could just disappear off, If it flew longer than a minute like the current plane did, the latest plane, say if it flew for 2 minutes and I had no control of it, yeah, that could go quite far. But also had a lot of drag, and because the thrust has to oppose the drag, the very little thrust produced by the engines struggle to get the airplane up to speed. So this new wing design uses a known aerofoil profile, which with the right airspeed and angle of attack... The profile I used was a NACA 4412. It's the same profile I use on my last vertical takeoff and landing plane. The reason why I use it is it has quite a predictable lift to drag and stall points through various angle of attack, so it's quite predictable. In theory, I can get a lift to drag ratio of 60-1, but that's when it's riding like just on the stall. Just before it stalls, it will produce that kind of value. So in reality, it doesn't produce anywhere near that because you're much more safer angle of attack. But yeah, I'm sure it's still way more efficient than my previous wing. Can achieve a lift to drag ratio of 60-1, so a little extra weight won't be much of an issue. And if you want to design a custom wing like this with your own aerofoils, I highly recommend checking out Onshape. I simply import the aerofoil profile from aerofoiltools.com, then with a few added design features, it's basically ready to print. These ribs are the same colour as my t-shirt. To fix the issues caused by the covering film, I decided to use a thin sheet of balsa wood to reinforce the leading edge. This stuff bends really easily, and if you take it outside in the British weather, it'll bend even easier. So much so that I could bend it round a 3D printed mould of the wing and pin it in place until it dries. Once dry, it holds the curved shape of the leading edge, and I can print some new ribs with a small step where the balsa will mount to. I then gave the wood a few coats of bright orange paint to make it look nice, which gave me some extra time to build a new wing structure. This new wing is similar to the previous one, but has much thinner ribs, as I'm hoping the balsa wood will add some strength. So this was a bit frustrating that I had to add these rods. I mean, it's part of the structure anyway, but I had to add these thin 2mm rods. They don't really weigh a whole lot. I think, maybe one of these is like 3 grams or something. So I think 6 grams for 2 of them. I'm not sure, I can't remember. They don't produce any span-wise strength. No strength along the span of the wing. They're literally just for compression reasons to stop those wingtip ribs like bowing inwards from the covering film, which it's kind of a bit annoying. Like, you wouldn't need it on a foam wing, but I guess it's just a necessary part of the wing structure. Strength, as well as some thin carbon rods to prevent the wingtips bending inwards. Once the paint was dry, I glued the balsa wood onto the wing structure with some thin CA glue, and the wing was looking really nice with the orange leading edge and grey ribs. Then the covering film can be applied to check how the aerofoil profile turns out, which looks much better. Also, with the thinner 3D printed ribs, this wing is actually lighter than the first wing. I say it's lighter, it was lighter by I think 1 or 2 grams, so technically lighter, but basically the same weight. And with 2 of these wings making up a 2-meter wingspan, it's over 3.5 times larger than the Airhogs plane. So we need a powerful engine to fly it. Fortunately, I've been developing 3D printed air engines for... I find it so funny watching this old footage back. I know I include it in quite a few videos, but basically that first version engine I managed to get running one evening. I blew into the topless cylinder head, and it managed to run. And I was like, I need to quickly get some footage of this running. So I grabbed that drinks bottle from the cupboard, cut 2 holes in it, glued some pipes to it. The absolute worst way to use a bottle as a pressure chamber. I didn't pump it up like above 30 psi or something like that because I was just scared it was going to burst at the holes that I'd cut. But and then the engine's attached to a random stick with some wire. But yeah, it's just funny looking back at that. A while now, and have tried many different designs such as spring-operated inlet valves, cam and pushrod valves, diaphragm actuated pistons, and the latest design that uses a custom moulded piston seal that expands under pressure to make the piston airtight, which is very similar to the Airhogs engine. And this engine has been a huge step up in performance compared to my older designs, producing 350 grams of thrust from an engine that only weighs 40 grams. The engine is very simple with only a few moving parts. High pressure air flows in through the top of the engine and is sealed by this ball bearing. Then as the engine turns, a small pin on top of the piston moves the ball upwards, opening the valve and letting... I do want to try build an engine with a slightly different piston seal. The reason for it is the seal contracts when the piston goes up, so there's no compression pressure, but when the piston's going fast enough, I'm sure some air gets trapped, like it can't flow around the piston quick enough. So it'd be quite cool to design a piston which is smaller diameter so that more air can flow around it. Maybe have like where is it? Like on this design, I have these channels down the side of the piston. Might be quite cool to print those so that loads of airflow can come around the sides and there's no compression as it goes up. And then also have a seal which shrinks more, so the expansion is a lot more, so that the upward stroke just has zero or hardly any resistance, because although I don't think it has a whole lot of resistance, if it saves a couple of percent here and there of the as the piston's going up, then it could increase the thrust a bit or the efficiency. High pressure air fill the cylinder, but this seal on top of the piston is a vital component to the engine's efficiency as it expands due to the pressure and seals against the cylinder walls. This causes the pressure to push the piston down, closing the ball valve and turning the crankshaft. Then as the piston reaches the bottom, the air flows out the exhaust ports and the seal contracts, removing any compression as the piston travels back up. Now the airworthy version of this engine is slightly different, but works exactly the same. It just has this 3D printed thread to attach to a plastic drinks bottle, and the air flows up this thin tube into the cylinder head. I also decided to buy a high quality propeller to hopefully maximise the thrust output. So this propeller, the main reason why I bought it, obviously it's much more efficient shape than the one I use on the thrust test stand and on my older planes. But also with the engine, as soon as it's flying versus just stationary on a test stand, the airflow reduces a lot of the load on the engine, so the RPM speeds up a lot. Because instead of trying to just accelerate, stationary air, it's got airflow moving into the front of it. So I bought this propeller because it's 16 inch, which is 1 inch larger than the one I use on the test stand. And also it's got a 6.1 inch pitch on the blades, which is a lot more. I think the old one is maybe like a 4.5 to 5 inch pitch. So having a 6.1, I was hoping would maybe keep a similar load to when it's stationary on a test stand. To hopefully keep it producing similar amounts of thrust. But yeah, I just thought it would probably be good to get a decent propeller as well. Spend all that time making an efficient engine and then put a rubbish $5 propeller on it. And surely the fact that this propeller comes with its own socks must mean it's good. And the fact it comes with its own socks. I mean, I can't remember how much the propeller costs. I think it was like £50 for a pair for two of those. So £25, what's that, $35? Which isn't a whole lot of money, but it is a lot for just one propeller. They are super lightweight though. I think it only weighs like 15 grams, which is really, really cool propellers. So I'm going to look after them and keep them in their socks. I know many of you are thinking, why don't I use CO2 cartridges instead of plastic bottles, as they can store far more pressure? Well, this CO2 cartridge is pressurised to about 800 psi, or about 54 times atmospheric pressure, which is a lot, but its volume is very small at just 21 millilitres. So if we let the CO2 gas flow out of the cartridge to equalise at 1 atmosphere of pressure. Now, I made a mistake in this, and I'm really annoyed that I didn't notice it earlier. But basically, I realised after everyone started commenting, The CO2 cartridge holds liquid CO2, not gas CO2. So my calculations here of it directly proportional to the pressure and the volume is not correct. When you expand this, which is a 16 gram CO2 cartridge, the gas expands to about 9 litres, not 1.1 litres. So it's about 9 times better. Even with the corrected expansion volume of 21 millilitres up to 9 litres, the fact it weighs the same as the bottle when pressurised, about 62 grams, and the bottle has 16 litres. Although my calculations were wrong in saying that the bottle was 14 times better, it's still nearly 2 times better. It's like 1.9 times more volume per gram. So yeah, I did make a bit of a stupid mistake in this part of the explanation, but the bottles are still better at the end of the day. We'd have just over a litre of gas, but if we pressurise a 2 litre drinks bottle to 120 psi, or about 8 times atmospheric pressure, we can store 16 litres of air. Yeah, so this is it here. So the silver bottle, which is the equivalent of what the CO2 canister would have, imagine 9 of them versus 8 of these 2 litre containers. So yeah, the bottle still wins, but I made a stupid mistake. This means we'd need 14 CO2 cartridges to equalise the storage capacity. So we wouldn't need 14, we would need 2 canisters to equal the bottle capacity of the drinks bottle. And considering the single cartridge weighs more than the bottle, the air storage to weight ratio is over 14 times greater. It is quite interesting though, when I calculated when the bottle's pressurised to 120 psi, it adds 20 grams of air, which, because I had 2 bottles, that's 40 grams of air, which is quite a significant amount. I don't actually have it here, but the onboard camera that I mounted on the plane weighs 35 grams. So that weighs less than the air that's inside of the plane, which is interesting little fact for the drinks bottle. So moving to CO2 cartridges would be a huge downgrade. But you know what isn't a downgrade? Trying out the Opera browser using the expensive task and Messenger apps. So to download Opera today. And thanks to Opera for sponsoring this video. So to increase the runtime, I'm going to mount 2 2-litre bottles back to back using a nylon bolt. This requires drilling out the underside of the bottles, which is the thickest part and shouldn't reduce its strength by much, as well as hollowing out the nylon bolt. But in order to attach the bottles together, I need to get the nylon bolt inside of the bottle, which requires cutting up an old arrow shaft and attaching a 3D printed socket, which perfectly fits the bolt and just squeezes through the bottleneck. This allows me to sandwich a large rubber washer between each bottle before tightening it down with a nylon nut, which should hopefully create an airtight seal. But before we test it for leaks, we need a way to pressurise it. The design I've come up with is a 3D printed bottle cap that has a small ball valve inside. And to fill the bottle with air, I can use this hose with a 3D printed latch attached. So a couple comments were asking why didn't I just use a regular bottle cap and then like a bike valve, like a Schrader or a Presta bike valve. And the reason is that I find bike valves just a bit of a pain, to be honest. Obviously that would be much easier because I wouldn't have to design all this latch and everything. But when you try and get like the bike pump onto it and like you wiggle it on and then you latch it and then you pump it and the air flows really bad if it's not, if the pump isn't properly pushing the valve open. So when you pump, you can't pump as fast. It sometimes leaks, and then when you gotta get it off and you gotta wiggle it off, and I didn't really fancy any of that, especially when dealing with these high pressures, 100 psi plus. When the bottles are on the ground, I literally just want to unlatch it and throw it. I don't want to have to be like trying to fiddle with the bike valve when this drinks bottle is at such high pressure. So I designed this, and it plugs straight into the connector on my bike valve, and just push it in, and it just works. Let's do it. This hose fits perfectly through the O-ring in the ball valve, and the latch locks into the bolts with a small turn. Once the plane is up to pressure, I simply twist the latch, pull the hose out, and the ball should seal the air inside. So I filled the bottles with water to reduce the potential energy if something were to go wrong, and pumped them up to 120 psi. I couldn't believe how much these bottles actually expanded when watching this video. It's fast forwarded a little bit so you can see the expansion, but it probably expands like probably about 10 mil in length, and then also the strengthening rings on the bottle when it's molded, they're like completely smooth, like you can barely see them, which is quite surprising how much the bottle flexed under pressure. And both the nylon bolt and the 3D printed filler cap held up without a leak. So it's time to build the tail of the aircraft. For this I chose to use balsa wood sheets, but this 4mm stuff is a little thick. So I ordered some 3mm sheets that were, believe it or not, shipped in a paper bag. So let's reduce the weight of the thicker sheets by drilling some holes. First with a small drill bit, and then with the large countersink bit to reduce. I really wish I'd got some 3mm balsa which wasn't broken, because this took forever. I think in both, what do you call it? They're not elevons on a VTOL. On both of the tail stabilizer and control surfaces, I think I drilled 70 holes total. It took ages. Splintering. And then finally with a 3D printed bit wrapped in sandpaper to make the holes nice and smooth. This reduced the weight by about 20%, and after a few coats of paint, by the way, 20% was like 2.5 grams, I think. I think it was 13.5 grams to start with, and it was 11 at the end. And there's what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 holes in each of the elevator bits. And then I think there's one less hole in the control surface, so 17 in that. Yeah, so 70 holes total to save, well, I guess it's 2.5 grams per thing, isn't it? So it saves 10 grams, I guess. Might have been worth it, I don't know. It can be laminated with the covering film to stop air flowing through the holes, because leaving a bunch of large holes drilled in the tail of an aircraft would be a bad idea. I then added control horns and attached the control surfaces with packing tape, as it's lightweight, flexible, and sticks well to the covering film. Now, I want this tail to be controlled via cables to keep weight away from the rear of the plane, so I used some spring steel wire as a torsion spring within the control surface. This idea isn't anything new, it's quite commonly used in gliders. In fact, this is a discus launch glider. If you haven't heard about these things, they're amazing. You hold them on the wing tip like this with your finger, and you swing round swing round and throw it like a discus, and you can throw it about 60 meters high. And my record flight with this was over an hour. Got up to 200 meters high. I could barely see the thing, but basically these have torsion springs in the tails. Probably can't see it, and then there's a very small cable. See, when I push it, it springs down. A very small cable in here. Very small cable right there, which runs to the front of the glider. Because the thing is with gliders is you don't have a heavy motor and battery in the front to bring the centre of gravity forward. So here's all the servos here. These are the aileron servos. These are the tail servos. The cable's going all the way to the back. So you need as much weight at the front as you can without adding extra weight. So having the servos at the front is pretty much necessary, which is also what I need to do on my air-powered plane, because the engine isn't that heavy. Like compared to an electric motor and well, especially a battery, the air-powered motor is really light. So keeping all the weight far forwards is a requirement. This causes the surface to be sprung loaded in one direction, which should keep the control cables in constant tension. Now you may notice there's only 2 tail fins here instead of a separate elevator and rudder, and that's because I've chosen to go with a V-tail design. This was a bad idea going for a V-tail design, however I did think it was going to be a bad idea when I was building it. Basically with a V-tail, it uses, obviously both of them go up and down for elevator control, and then to turn it, to do rudder control, they go in opposite directions. And because this plane doesn't have ailerons, in order to turn, it has to use the rudder. But say if you want to turn left, the way the flaps go in opposite directions to turn the tail to the other side, it basically causes the plane to roll in the opposite direction that you want to turn. So you want to turn right, and the plane goes left. You want to turn left, and the plane goes right. But because this wasn't going to be a high performance maneuverability plane, it was just meant to be lightweight and aerodynamic, I thought I could get away with a V-tail. But from the flight footage, you can see it sort of wobbling around in the sky a bit. So it would fly better with a conventional tail, but this was just to save weight and drag. I then printed this odd looking part that the tail boom will mount to, and I can attach servos here to control the tail, which works really well once the cables are attached. This central hub also mounts to the bottles with a flexible printed ring, and a small bracket on the tail boom to complete the plane's fuselage. Now all it needs is the wings to be attached to these points, and we have a completed plane. Let's take it out for a test flight.
Right, we're at 60 psi, but I can hear a leak out of the rear bottle cap. It's not a good sign because I pressure tested this already.
What's funny is every air-powered plane video I upload, I get comments going, "Tom, you need to do more exercise. You're always out of breath when you fly these planes." And I'm like, "Yeah, do you know how long it takes to pump these planes up?" It takes. What's funny with the pump that I have is almost exactly volume matched to the pressure in the bottle. So one pump almost goes up exactly 1 psi. Because I would count. I go 10 pumps, 10 psi, 20 pumps, 20 psi. So to get to 100 takes 100 pumps. However, on this first test, the reason why I'm so out of breath on this is because the leak, above about 70 or 80 psi, the leak was almost equal to the speed I could pump at. So I was just like pumping as quick as I could. I didn't edit it into the video, but I was pumping as quick as I could just to squeeze the pressure up a bit. So it was pretty much just a cardio gym machine, but a bike pump version.
Okay, quickly release that. Here goes nothing. Check the controls and start the engine.
You can see there it's wobbling a bit in the sky, and I think it might do it around here. When I start to turn, it's sort of it wobbles.
That's brilliant. And can I land it? Can I land it? It worked. It worked. It looks like the propeller snapped off though. Let's go and inspect. Right, so the crankshaft snapped.
I did spend a few days actually designing propeller savers on lots of small like aerobatic model aircraft. They have these things called prop savers where it's the propeller mounts to the motor with a rubber O-ring. But I was running into issues because the torque output of the engine is not constant like an electric motor is, and it uses the propeller as a flywheel. So every time the piston would like do its power stroke and then it would do the freewheeling to push the piston back up, it would cause the propeller to knock back and forth. Even though the propeller saver had two like pins in it which lock into the propeller holes, it would just a tiny bit of tolerance would cause a wobble, and it would cause a horrible knocking noise when the engine would run, and also the engine wouldn't run the performance of the engine wasn't as good, probably because when the piston was going up and hitting the ball valve, it was like knocking the propeller and all sorts. So in the end, I had 1 day to do this test, which came up really quick on the weather forecast that there was no wind, and I didn't have time to design anything that would properly work. So I ended up just bolting it on and just hoping it didn't snap, but it did snap.
But that is definitely the longest air-powered plane flight I've ever achieved.
So now that the record flight time for a 3D printed air-powered plane has been increased to 31 seconds, I took to Instagram to ask how long you all reckon it will fly for, and the majority of you chose more than a minute, so I can't give up just yet. To increase the flight time, I fixed the leak in the bottle cap by reprinting it with a larger O-ring, and it was ready for another test. That's about the speed I was pumping it on that first test when the air was leaking out. So that's why I was so out of breath on that last one. And I was tired on this one too.
And 100. One for good luck. Please run properly. Oh, the battery's come off. Come on, we can climb, we can climb. Come on. Yes!
Here's the wobble again. You see it swaying around as it's
Oh.
floating through the air.
Oh, that's so much better.
I think if I'd climbed a bit higher, it would have flown for longer, but it wasn't seeming to. For some reason, it couldn't climb any higher. And the thing is, the more I try and climb, the more drag it produces. So the slower it flies. And I didn't have it on this test, but in later tests, I would find that like if I pitch up and like almost stall it, reduce the airspeed, the engine revs would drop because it'll put the engine under more load because it's trying to accelerate the plane. So I found it better just to keep, get it up a little bit and just keep a constant altitude so that the engine would run at better RPM.
It's coming down. The battery fell out. Can you see it hanging?
Here it is. I've got the plane at like a higher angle of attack, and you can see it just sort of, and then it stalls, just misses the ground.
Oh, we have to do another one.
You can see here I've got the propeller in my hand again because it's this time I actually put a longer bolt through and it snapped the whole crankcase off the front instead of just a crankshaft. But I edited all that out. I did actually come up with a propeller saver. It was more of like a disposable breakaway piece that would hold the propeller to the shaft. So it was 3D printable. I could print 10 of them in an hour. And it just had these small tabs which would make sure the propeller was completely locked to the shaft so there was no knocking. But then on the landing it would just snap it and I'd just replace the part. And that worked really well, but that wasn't until after this day.
Oh, yeah.
For the next flight, I decided to add a small onboard camera, but due to my excitement of the previous flight, whilst tightening a bolt, I accidentally pierced a hole in the bottle.
You see that? Oh, it's just hissing out that hole.
Fortunately, I had some spare bottles, so it was an easy fix. Though throughout this period of adding the onboard camera and bottle replacement, I forgot to do one last vital check. And that was whether I'd pushed the tail boom back into its mount properly. Because this means the control cables are too short, causing a lot of... I did a control check on every flight apart from this one, and that's always the way it goes. I would have done a control check, but I was so stressed out about the piercing the bottle, replacing everything. To get the onboard camera mount on, I had to take the tail boom out anyway. And it was just stupid mistake under running on adrenaline and a bit of stress. And I just missed it. Up elevator trim. It happens.
3, 2, 1. Oh, no.
This may look like the end of this plane. It looks so much worse than it actually is. Which I suppose is good for the YouTube video. But yeah. I did think it was destroyed. But after a quick depressurization, I was surprised to see how little damage there was.
The only damage, apart from this 3D printed bit here, as far as I can see, this wing's fine. Just this wing here, which a little bit of packing tape, that'll fix that.
So I fixed the wing with a small patch of tape and reprinted a new central hub, which I honestly reckon saved the plane when it snapped. I think the central hub did save a lot of the impact force. It didn't snap where the wings mount, so I guess it just removes the weight of the tail on it. And then maybe the bottles come loose as well because they're bolted to the tail. But I do think I could have shaved a lot of weight off of the wings because they survive. I mean, it probably nosedived from like 4 meters up, maybe 4 meters up, and landed directly on one of the wings. And the fact there's like no structural damage apart from a little bit of film on the trailing edge. Yeah, I probably could make them a bit lighter and weaker. And by the following day, it was back up and flying. See, this shot is me trying to get the plane as high as I could. It didn't fly for as long though, because it takes forever to get up to that altitude. And then I think it was on this day I was flying, and there were some thermals, and I managed to get it in a thermal for a bit, and it kind of went up, and then the air started running down, and so it was just gliding, and then it got into, I don't know the name, but like where the thermals sort of go up, there's like a down bit as well on the outside, then it goes up. I fly in thermals quite a lot with the discus launch glider. But with this thing, it doesn't turn quick enough to stay in the thermal. So you go up in the thermal and then you suddenly go, whoa! And yeah, and then I was trying to keep the altitude, so I was stalling on the way down and everything. So I didn't fly for very long, but it does look quite cool flying up that high. Though I've yet to beat the 1 minute 22 second flight record again. Mostly because it really struggles in the wind.
Oh, no. Watch out.
This is funny because my dad's filming and my mum was standing just behind my dad, and this was heading straight for her. I'll see if I can pause it. There she is. You can see the back of her head. Okay, the plane's a bit further away, but from my perspective, I thought it was gonna hit her. Yeah, there was just no control in that wind. It was awful.
It's way too windy.
I have had a few flights over a minute, but I think it needs some weight shaved off before I get near the 2 minute mark. Even if I can reduce the overall weight of the plane by about 10%, that will be enough to add another. See, that onboard shot was with the Insta360 Go, which you can see mounted just behind the wing, like above the bottle cap. And that's the camera that weighs like, I think it's 35 grams. So it weighs less than the air in the bottles when they're pressurized, which is crazy. Bottle, which will help extend the flight time. Thanks. And here I landed the plane with the propeller saver, the breakaway one, but the propeller was already stopped. So I think that was probably one of the only flights I landed without breaking something, which was quite cool for the onboard shot, to be honest. Thanks for watching. I thought this bit was funny because the wind starts the engine up again just as I end the video, which was quite cool. So yeah, that's the deep dive of this video. I think I've spoken about most of the things. I hope you find that interesting. Maybe I'll do one of these videos every time I upload a main channel video, depending on how much you guys like this. It's probably quite a long video by now, isn't it? Yeah, quite a long video. I should probably end it quickly. Thank you very much for watching, and I'll see you in the next project.